Today, we're going to talk about a brilliantly simple idea that managed to solve one of the absolute biggest problems in AI. It's a technique called LoRA, and it really shows how a tiny update can completely change the game for these giant models.
So, this is the big question, right? You've got these incredibly powerful models, like GPT-3, but what if you want to teach it something new, something specific? The challenge is just massive. How do you go in and make a precise little change to something so gigantic without needing your own personal supercomputer? This isn't just about not having enough computing power. It's a problem of pure scale. The size of these models creates this huge logistical and financial headache. And to really get a handle on that headache, you've got to look at the numbers involved.
Just let that sink in for a second. $175 billion. That's how many individual knobs or parameters have to be tuned inside a model like GPT-3. It's a level of complexity that's almost impossible to wrap your head around.
And all that complexity? Well, it hits you right in the real world. Just one custom version of that model takes up over 350 gigabytes of VRAM and storage. Now imagine your business needs 10 different custom versions. All of a sudden, you're not talking gigabytes, you're talking terabytes of data. It just gets way too expensive, way too fast.
Okay, so of course, a lot of really smart people have tried to find workarounds for this. There were some pretty clever methods to make the whole process more efficient, but as you're about to see, every single one of them came with a pretty big catch.
So there were basically two main schools of thought. On one side, you had full fine-tuning. It works for sure, but you're right back to that 350 gigabyte problem every single time. And on the other side, you had adapter tuning, which was a lot more clever. Instead of changing the whole model, you'd just slot in these small new layers. But it had a hidden and really critical flaw. And this quote from the original research paper really nails the problem. Because those adapter layers have to be processed one after the other, sequentially, they add a little bit of extra time to every single request. This creates something called inference latency, basically a delay before you get an answer. And for any real-world app, that's just a total deal breaker. You can't have that lag.
And this is where LoRA, which stands for Low Rank Adaptation, comes onto the scene. It's just an incredibly elegant approach that gives you the best of both worlds, all the efficiency with none of the latency.
Okay, so here's the absolute genius of it. LoRA freezes the entire 175 billion parameter model. You don't touch a thing. Instead, you inject these two very small new matrices, and by only training these tiny little matrices, you can steer the behavior of the giant model without ever having to change its core. Let me break this down with an analogy, because this is really cool. Think of the giant pre-trained model as a priceless masterpiece painting. You can't touch it, you can't edit it. That's step one. Now, LoRA is like taking a perfectly clear sheet of plastic, an overlay, and placing it on top of the painting. That's step two. Then you use a special pen to draw your changes right onto that plastic sheet. That's step three, training the tiny matrices. It's super fast and cheap. But here's the magic trick. For step four, when you're ready to show it off, you can mathematically merge your drawing from the plastic sheet right into the painting's data. You get a new final image with zero extra layers and absolutely zero extra delay.
It's a really beautiful idea, right? But does it actually work in the real world? Well, the data tells the story. And honestly, the results are kind of mind-blowing.
Just look at the difference here. This comparison is for a model called DeBerta. To fully fine-tune it, you have to train 1.5 billion parameters. But with LoRA, you're only training 4.7 million. We're not talking about a small improvement here. This is a whole different ballgame.
But here is the absolute kicker. You'd think with that huge reduction, you'd take a big hit on performance, right? Nope. In fact, on this benchmark, LoRa's performance was actually a tiny bit better than fully fine-tuning the entire model. And that's the moment it clicks. This isn't just a clever workaround, it's actually an improvement.
So let's just hammer home how big a deal this really is. With models like GPT-3, LoRA can slash the number of parameters you need to train by a factor of 10,000. It just makes the whole process so much more manageable. And that, of course, means you need way less hardware. The GPU memory you need gets cut by a factor of 3. All of a sudden, high-end AI customization is back on the table for way more developers and researchers.
And here it is, the final, crucial blow to all those old methods. Remember that latency problem? The delay? Well, because LoRa's changes get merged right into the model, it adds exactly 0 extra delay. It is just as fast as the original. No compromises. So what's the big picture here? Well, this isn't just some neat technical trick. It literally changes the entire playbook for how we develop, deploy, and personalize artificial intelligence.
I mean, the stuff that LoRA makes possible is just incredible. Because the custom updates are tiny, we're talking megabytes instead of gigabytes, you can store thousands of them. You can switch an AI's skill or personality in an instant. It makes AI customization cheap, fast, and scalable in a way that was just a pipe dream before.
And look, this isn't some pie-in-the-sky idea from a research lab. LoRA is so good, so effective, that it's already a standard tool in major AI libraries like Hugging Face's PEFT library that stands for Parameter Efficient Fine-Tuning. It's become the new default for a reason.
So we'll leave you with this thought. The incredible success of LoRA proves that you can fundamentally change a 175 billion parameter model by just tweaking this tiny, low-rank slice of it. It just begs the question, what does that tell us about how these giant AI brains actually work, and what other simple, powerful secrets are still hiding inside?